Hello, in this video we're going to be talking about the sampling mean of a normal distribution, and we'll see that actually this thing called the sampling mean in itself is normally distributed. The target really is for probably further A2, although for further A2 maths. However, single A2 may find this useful, but it probably goes a little bit further than you need to know. But you do need to know the principle of sampling mean of a normal distribution. We're going to do a few proofs and a little bit of a proof, sorry, and I'm going to do a little simulation because sometimes with stats it's easier to visualize things intuitively if we do simulations rather than the pure mathematical approach. So what we mean by the sampling distribution at x bar, so with the top on top, is basically, suppose you were taking n samples from a normal distribution, so x1 is the first sample from this normal distribution, and x2 is the next sample, x3 is the next sample, and so on up to n, and you were to find the mean of all of these samples, then what it makes sense in the end that you're going to find the mean is going to, the expectation of the mean of this distribution is going to be the same as the original normal distribution which we were dealing with. But what about the standard deviation? And that's what we're going to, or the variance, that's what we're going to talk about now. The mean will be the same, but the standard deviation will be different. And it's kind of important, well, probably important to appreciate that we're doing this, we're basically taking these samples over and over and over again. And then that distribution itself will be normally distributed. But as you'll see, the standard deviation, what we actually call the standard error, is not the same. It's actually equal to this over the square root of n, and this is called the standard error, and that basically means that is the standard deviation of the sampling distribution. Now this is all a bit theoretical at the moment, standard deviation of sampling distribution, and I think, as I say, it's nicer if we see this in a bit of a, because it's actually fairly intuitive, believe it or not. I probably lost a few of you already, but it is pretty intuitive. So before I do the proof of this, because I think this is definitely not required for single maths, the proof of this, by the way. In single A2, you do need to know the standard error, what that means, and you do need to have the idea of a sampling distribution, sampling mean of a normal distribution, and know that itself is normally distributed. And in fact, as I said, we can say the distribution of the sampling distribution will be normally distributed with mean mu, and standard deviation, which we call standard error, for the sigma over the square root of n. In fact, we'll probably be careful because that's the standard error, so that we could write it like that, or if we prefer, write the variance sigma squared over n like that. Okay, so as I say, I've just told you that really. We've defined what sampling distribution is. It's basically we're taking n lots of samples from this distribution and repeating it over, and then that itself will give itself its own distribution, which will be normally distributed with the same mean, but actually a tighter standard deviation. And I say, before I do the proof of this, I don't really perhaps think it'd be nicer to actually look at a few simulations. Okay, so give a shout out to a guy called Steve Phelps, who I basically Googled this and looked under GeoGebra to see what will come up, and he's come up with two nice simulations for this. The first one is basically sampling from the standard normal distribution. A sample of 10 is taken, and the mean of those is taken. So the orange dot is the mean of each sample. So we've got samples of 10. And on this one, there's quite a lot of, notice this one, just by chance, a lot on the right hand side. But what the effect is of taking the mean of a sample size of 10 is that the extremes are kind of taken out. So this kind of intuitively gives us an idea that the standard deviation or the standard error for the sampling distribution is going to be tighter than the standard deviation of the original parent distribution, because you're basically kind of taking out the extremes by taking the mean of each of the sample of 10, and so you're not likely to get many around this end here, around the ends, because you would have to have, most of your 10 values to be around the end on each side. So it kind of takes out the extreme, and sooner or later it's going to resemble, I mean, it doesn't look like much at the moment, but what I might do is at the end see what happens at the end when we've done the algebra, and come back to these simulations to see what's happened. Right, the other one, this is one I've done earlier, and it's and I will restart it when we get going again. This is a sample size of 4, so we can't see the dots dropping down like we did with the other one, but we can see that that indeed it's beginning to look normally distributed. Notice the mean of our sample is now 50.04, and our standard deviation is 5. It's halved. So that's kind of intuitive. That from kind of justifies from obviously it's not done algebraically justifies, but it makes sense that the standard deviation is half, because the sample size is 4 and the square root of 4 equals to 2. Okay, so what I'm going to do is clear the data, and we'll see. And we can see the dots kind of as they are building up. And obviously at the moment, the standard deviation is 3.854, 50.96 and 50. Standard deviation isn't quite yet resembling the actual standard deviation, because it will take a while to settle into the actual sampling distribution, to kind of settle into what the distribution is. And of course, we can carry on this forever, and it will become what's known as it becomes known as what's known as the sampling distribution. Okay, so I will come back to the algebra now, and maybe come back to that later and see how it's looking. So in this algebraic demonstration now, algebraic proof, let's do with the mean, because that's easier, and it's fairly intuitive. The expectation of the sampling distribution will be equal to the expectation of, and let's rewrite this as, x1 over n plus x2 over n plus x3 over n, and so on, up to xn over n. And using normal expectation algebra, you can use the expectation of e to the ax 1 plus, let's just say e to the ax plus by, say, we can just use it, that general result is equal to e to the x plus b e to the y. And we can just say, well, x1, and we can x1, x2, x3, x4 are our distributions. So we can just use this idea to say that's 1 over n e to the x1, 1 over n e to the x2, plus, and so on, 1 over n e to the x3, up to 1 over n e to the xn. So that equals to, right, so we can go back to e to the x1 plus e to the x2 plus e to the x3 all the way up to e to the xn. And that equal over n. Now obviously by definition, remember x1, x2, x3, x4 are all just the observations from the original, are all kind of the same, have the same distribution of the original normal distribution. So the expectation of those is mu. So we've got n lots of mu. So that's n mu over n, which is equal to mu. So the expectation of the sampling mean is itself the same as the original distribution, which is intuitive, of course. That's right. Now the standard deviation or variance. Let's do quick variance, which then leads to this idea of this standard deviation, standard error. So we want the variance of x bar, right, is equal to the variance, and I'm going to write it like 1 over n x to the 1 plus 1 over n x to the 2 plus 1 over n x to the 3 and so on. Let's write it like that. And now we can use the kind of, this is basically an adaptation of the idea that the variance of ax plus by is equal to a squared var x plus b squared var y. So in other words, we need to square each of the n's here. So that's 1 over n squared var x1 plus 1 over n squared var x2 plus 1 over n squared var x3 and so on up to x to the n. Okay, so let's rewrite that over a common denominator. That's var x1 plus var x2 plus var x3 all the way up to the final one, var x to the n, all over n squared. Now the variance, again, x1, x2, x3 all have the same distribution as the original normal distribution. So that's like sigma squared all the way along. But we've got n lots of these. We've got n times. I'll write that on both of these. N times. And here we had m times as well. So we have, that's n sigma squared over n squared, so that equals to sigma squared n. So the variance of the sampling distribution is sigma squared over n. So therefore the standard deviation, let's write in x bar, of sampling distribution, standard deviation of sampling distribution is the square root of that. So that equals to the square root of that, which is, and we're going to see this a lot, and in single maths we see it, and in further, it's quite fundamental. And this is called, we have a special name for this, which I've already mentioned. This is called the standard error. Just to distinguish it from the standard deviation of the original distribution. Okay, so that's it. Let's go back to the actual simulation, the second one, to see how it's looking. It's a fantastic simulation, this. So well done to Steve for coming up with this. So Yeah, the only thing I would have liked to know is what actually the sample size is. How many kind of these samples? Remember, what's happened is we've taken a sample of 4 each time and found the mean, and each of these pink dots represents one of those. And that when we do this kind of indefinitely, that's called the sampling distribution of sample mean of the original normal distribution. And we can see that the mean is very similar, not going to be the same, of course. Theoretically, as we go to infinity, it'll be the same, and the standard deviation will be equal to the square root of basically it'll be half, because it's the square root of 4 is equal to 2. Okay, that's nearly it. I was going to finish there, but there are one or two things I thought about which I'd like to mention with you now. First thing, as I've mentioned before, is just a kind of exam kind of consideration. This is for England and Wales, Northern Ireland students who are taking A levels. You do need to. You wouldn't need to know the proof I've shown for standard single A level, but you do need to know the idea of the sampling distribution and what it is and how I've described it. Well, you do need to know that. In further, you do need to know the proof. You should really be able to understand the proofs that I've done. And just before I go, this square root of n is quite significant, because if to the standard deviation to standard error involves a square root. So in other words, we need n to be equal to 4 in order to halve the standard error. We need n to be equal to 9 in order to third the standard error. And you get the idea. In order for n to be if we have n is equal to 100, our standard error is going to be 1/10 of our standard deviation. Okay, so that is quite significant, because what we're coming on to is doing hypothesis testing and talking about sample size. And this kind of what the economists call the law of diminishing returns is quite significant when it comes to deciding sample size, because 100 is already quite big, but we've only got 1/10 of the original standard deviation. So if we're trying to make inferences about the mean, it's desirable to make the standard error as small as possible. But because the relationship involves the square root, we have to throw a lot of it in order to reduce the standard error. We have to do a sample size of 4 times as big in order to reduce the standard error by a half, and that is quite significant when we're deciding about what the sample size is, and which is why sometimes it can be quite costly to choose big really large sample sizes in hypothesis testing, because the gain is relatively marginal. But of course, we do need to take samples, because the larger the sample, the smaller the standard error. But it goes down at a kind of decreasing rate, standard error, which is, so it's desirable to when we're doing hypothesis tests, to have the standard error as small as we can, but there's cost implications because of this thing that the economists call the law of diminishing returns, and this thing called this square root sign on the bottom. Okay, so next video we'll actually go into the hypothesis testing, and I'll be assuming that you basically have understood at least this idea of the standard error, not necessarily the proofs, and that you've kind of understand the basic principle there, and we'll be doing some hypothesis testing with the sample mean. Okay, thank you, bye.